Hi, I'm Matthias Beck. I'm one of the authors of Computing the Continuous Discretely. And in this video, we will continue our discussion about generating functions. We will concentrate on partial fraction expansions. And I encourage you to watch this video before you get into the gory details of section 1.3 in the book. Okay, let's get started. You probably remember partial fractions from your calculus class. So way back there, you had a function, let's say, of the form 1 over 1 minus z squared times 1 minus z, you see here, and you expanded this into partial fractions. Here it is. And the reason why you did this back then, well, one reason was you were integrating functions like that. So let's say we're integrating this with respect to z. And the point of partial fractions is that this function a priori is hard to integrate, but the integral of a sum is the sum of the integrals. So once we have partial fractions, we can try to integrate each summand over here, and if we can do that, then we can put those integrals back together as a sum, and then we have an integral of our original function, and that's exactly what happened. So what we do now is we follow a very similar principle, except that we don't do partial fractions to do integration. We do that for a generating function calculation. So what I want to compute the generating function of a function like this. And again, I'm in the same situation. I don't quite know how to do that. But if I can somehow compute the generating function of each summand over here, then I can then sum up the generating functions, and I will get the generating function of my original function. And so I will use exactly the same principle that you saw in calculus, decomposing a function into partial fractions to be able to do computation, except I will do that on the level of generating functions.
Hey, Kumi, what do you think about partial fractions? What do you think? You like them. Yeah, that's what I thought. You like them too.
Okay, what we're going to do now is we use this technique in several ways with generating functions. In the first example, I will compute the exact formula of a counting function. So this example is about partitions. I mentioned those in the previous video where we had compositions. So a partition is very similar to a composition. Again, we are given an integer k, and we want to write it as a sum of positive integers m1 through mn. But as opposed to a composition, now I want to disregard order. So, for example, I might have the partition 2 to 1 of the integer 5. And then contrary to the last video, I will not be able to reorder that and say I also have the composition 2 plus 1 plus 2. The way I'm going to enforce that is I will assume that my parts, the parts of the partition, will be ordered in the sense that m1 is bigger than or equal to m2, which is bigger than or equal to m3, and so on. Okay, so let's again compute an example of a counting function. So maybe I'll call that counting function p2 of k. This is the number of partitions of k into exactly 2 parts. We will compute the generating function, And we will do that from first principles. So it's a bit similar to the previous video. So let me, this is going to end up being a double sum. Let me look at all possible ways of writing z to the m1 plus m2. So up here I have a partition. So there are constraints on m1 and m2. So my m1 is bigger than m2, so I will make this the constraint on the inner sum, which is over m1, and then my outer sum is over m2, and my constraint here is just that it's bigger than or equal to 1. Okay, we can take this apart. So my outer sum is over m2. My z to the m2 does not depend on the inner sum, which is over m1. And so what's left in the inner sum is z to the m1. Okay, so we recognize here another geometric series. So remember, m1 is the summation variable. So this is a geometric series that starts at m2. So we have z to the m2 over 1 minus z. And so now you can see what happens. There's a constant 1 over 1 minus z that comes out of the sum, and then what's left is my sum over m2. And then in here I have two terms multiplied. They both look like z to the m2, so I have a z to the 2m2. Okay, so the sum is a geometric series in the variable z squared. Z squared over 1 minus z squared. And don't forget I had my factor 1 over 1 minus z outside. So this is our generating function. Okay, so let's compute with this. Conveniently, I use exactly the partial fraction expansion of my calculus example. So I have an extra z squared here, but then I can use exactly this partial fraction expansion. And I will rewrite this just slightly. So I have a 1/2, and I will rewrite the first term as 1 minus z squared. And the next term, I will introduce a minus sign because I want to write this as 1 over 1 minus z. And the last term I will write as 1 over 1 plus z, because by now you will not be surprised by that. Each of these terms I will interpret as a geometric series. So here's a geometric series on the nose. Back here, what I see is a geometric series in the variable negative z. And up front, if you think about this for a moment, you see the derivative of a geometric series. So if I differentiate the geometric series, I get a k times z to the k minus 1. Okay, so let's put this all together. So I would like to write this as one formal power series. So I have a z to the k. So what I will have to do is I will have to adjust my summation index for the first series. So what we have is there's a 1/2, and then this k becomes a k plus 1, because I want to have a z to the k outside. From the middle term, I get a 1/4. And then from the last term, I get a 1/4 times minus 1 to the k. And so let's not forget we have a c squared outside. So I can move this over here and increase my z to the k to a z to the k plus 2. But at the end of the day, I want to have a z to the k, so what I'll do is I'll do another reindexing. my k starts at 2. And so the terms of my generating function now look like 1/2 to the k minus 1. Nothing changes with a quarter. And then I get a quarter times minus 1 to the k minus 2. But that's the same thing as a minus 1 to the k. So we started with the generating function for this partition counting function P2. And so that means here it is. So this is an exact formula for the number of partitions of k into 2 parts. Let's maybe make a sanity check. So let's see what happens for k equals 2, which is the first value here. So for k equals 2, we see 1/2 times 1 plus a quarter plus another quarter, so that's 1. And indeed, if we want to have a partition of 2 into 2 parts, there's only one way to do that, namely we have 1 plus 1. I wanted to show you one other example that's in the book. In fact, it's in the section 1.1 where we talked about Fibonacci numbers. We did a partial fraction expansion there, so I encourage you to look at that. So here's the result. So let me remind you, when we had the Fibonacci sequence, we considered the generating function, realized that this is the rational function z over 1 minus z squared. And if you do partial fraction on this rational function and then collect coefficient, you get this formula over here for the kth Fibonacci number. So this is a famous formula. But the reason why I wanted to point this out over here is this partial fraction in this case gives you a very nice approximation, namely, well, up to the constant 1 over root 5 up in front, you have 2 terms. So one term is here that we take to the kth power, that's the golden ratio, and the other term is sort of the conjugate of the golden ratio over here. And what I would like you to know is that this number over here is in absolute value less than 1. And so you have an exponential as a function in k. This is an exponential function with a base that's less than 1. So as an exponential function, this goes away very, very quickly. What this gives you is it gives you an approximation of the kth Fibonacci number in terms of this first term. So the kth Fibonacci number is roughly 1 over root 5 times this golden ratio to the kth power. And this approximation is very, very good. If you take a computer algebra system and plug in this number, you will see, after the first few k's, you will see numbers that are very, very close to an integer, and that integer will be the kth Fibonacci number. So this is an application of partial fractions that allows you to not only give you a closed formula, but a very useful closed formula where you can say something about asymptotics. The last thing I want to show you in this video is what happens when we apply this to what's called the restricted partition function. So now we're getting back to the book, and so this is the main topic of chapter 1, is this function that we p sub ab of n. So a and b are fixed positive integers. Might as well assume that they're relatively prime. And so what we're doing now is we're counting the number of partitions of n. So if you look at this last expression in my definition, so I think of this as a way of expressing n as a partition whose parts are A's and B's. So I'm fixing A and B, and I'm allowing as many A's in my partition as you'd like. So I'm allowing repeated parts here, I guess, and as many B's. And so if I have K A's and L B's, then what I'm doing is I'm writing N as this linear combination A times K plus B times L. And what we're doing in this book is first we compute the generating function, but then there's sort of a twist. So what we want to do is we want to extract an actual formula out of this generating function for this restricted partition function at n, and this is described in detail, but the technique that we're using is we're sort of taking the generating function and dividing by an extra z to the n, and then expand this new rational function into partial fractions, and the actual partition function, the actual restricted partition function, will be the constant term of this new expansion. And so if you do partial fractions, it looks like this last line on the screen over here. So these coefficients A1, capital A2, and so on, those are things that one has to compute in terms of partial fractions. But I wanted to give you a very quick idea of what this is good for. So there's the first part in this partial fractional expansion. So this part comes from the pole of the rational function at 0. And if you think about computing a constant term of a function that's expressed, I shouldn't say a Taylor series, but as a Laurent series about z equals 0, then none of these terms contribute. So we might as well exclude that. Then we have two terms over here that come from the pole at z equals 1. That's a double pole. And we can compute those coefficients b1 and b2. And then there are some terms over here. They come from a-th roots of unity and b-th roots of unity. And if I assume that a and b are relatively prime, then all of these non-trivial roots of unity are simple poles of my rational function. And so again, I can compute these coefficients that we call ck and dj. And then if I want to compute the constant term of my function f, again, I can ignore this first part and just compute the constant term over here. I wanted to briefly show you this because the point of the partial fraction decomposition in this example follows a similar philosophy to the previous two examples, where you have some function, you want to compute something, in this case a constant term of this function f of z, and it's hard. So what you do instead is you compute a partial fraction expansion, and you can compute the constant term of f as the sum of the constant terms of the terms in the partial fraction expansion. And then what you can see is there's first some terms in the partial fraction expansions that you can ignore because they don't contribute to the constant term, and then some other terms that, for better or worse, you have to compute. But for those things, in this case, we can do it by hand, but you could also use a computer to calculate these terms, and then you get a closed formula, and you will see this in all its details in section 1.3 in the book.
High five.